So far, in this series of videos, we have been speaking at length about first the history of artificial intelligence, then the history of deep learning in particular, with history being a bit of a stretch as the whole thing mostly began in 2015. And then we have given detailed definitions on what deep learning is and how to use it, including code that you can find online and in the notes of these videos that tells you how to prepare the data to use deep learning networks, how to fit models to data and what that means with first simpler models and then with more complex ones with real deep learning models. And we have spoken a little bit about the results that we get and how to interpret them. In this video, I wanted to finish this series by speaking about deep learning today and its, let's say, wider social implications. There are quite a lot of news around about deep learning, what deep learning can mean for the future of our society. I honestly think most of that is noise, but some valid concerns are raised, and I wanted to speak about that a little bit. Before I do that, I will remind everyone that I'm not really a deep learning expert. I'm, I would say, an advanced deep learning user. I'm used to working with different computer-based technologies to solve different practical problems, and deep learning is just the last one that I'm using. So I'm not, let's say, at the forefront of this thing. I'm just a user, probably with some more depth than most people. Okay. As we are seeing, deep learning has become very popular in many areas, especially in research, but also there are quite a lot of deep learning based products, and we will speak about those a little bit later, because it's very effective and it gets very good results. And it's also very easy to use, and that results in very frequent black box use, which means that the data is prepared in a certain way, following a kind of a recipe, and then deep learning networks are used without deep knowledge of what they are doing. And even that works surprisingly well, but that also leads to some confusion and some problems that I want to detail a little bit. I think what it mostly leads to is a wrong impression on what deep learning is. So I will also spend some time giving my view on what deep learning is, and very especially on what it is not. We have seen so far that deep learning algorithms can be used to, for example, play Go very well, or win the famous ImageNet competition. But deep learning networks are also being used in a variety of areas, and you don't need, let's say, first level research department or company to perform deep learning research or to use deep learning algorithms. And I wanted to give you a bit of a context on the example that we have been using for the training and the preparation of the data. This problem about classifying the subalpine bushes in Zhao Mountain. As I said before, this has some ecological importance and for the study of the effects of climate change and for the study of the health of the site itself. So the point is to be able to classify these images from 6 different bushes that look quite similar, actually, effectively using deep learning. Okay. This is a simple research project that we carried on here in Yamagata University, and one of the things that we wanted to do was to compare the performance of the deep learning networks to the performance of humans. We wanted to keep an eye on the practical usability of the whole thing. If we develop super cool algorithms, but they don't bring anything new to the table, they don't contribute to the research, then, well, perhaps it's not worth doing practical research with them. But in this case, we were able to see some nice differences that I will tell you about. These slides, by the way, were done by my student Komo Moritake for his master thesis. So thanks to him. First thing that we did in this problem was to gather a group of people with different backgrounds in computer vision or in forestry and ask them to solve the problem, to classify manually the bushes, the images of the bushes, into the 6 classes. And the first thing that we realized is that this was a very difficult problem for humans. Here we have the computer vision beginners and the computer vision experts. The forestry beginners are the forestry experts, and this is the accuracy with what they could solve the problem. And some people really had trouble with that. 13%, 37, 40, 51, 43. It is important to say here that these percentages, which appear very, very low, are perhaps not so much. If you have a binary classification problem where you either have to assign any image to 2 classes, for example, cats and dogs, then if you do that randomly, your expected result is 50%. But in this case, we have 6 classes, so random classification should get about 16%. Okay, so some people were really unlucky with their classification and really did not get the problem and got less than they were expected to get randomly. But some other people got in the high 40s or in the mid 50s of classification accuracy. So these people were able to really understand the problem and get much better results. Not only that, the main problem we found was finding the exact class, but there were 2 big groups, the deciduous and the evergreen bushes. And if we just consider correct things that were in the right group, then humans were able to do that much better, up to 90% accuracy there. Okay, so the problem was not finding out what general group every bush belonged to, but finding the exact class, and that was very, very difficult. 55% success for humans. Then we decided to check this against the performance of deep learning classifiers solving the exact same problem, and we tried a few of them, and we got here are, remember, the classification accuracies of the human experts, and we see here the 2 big groups, the evergreen and the deciduous, and that the most confusion happens within the group. This is a confusion matrix. This means that these are the predictions, the bushes that were predicted to belong to class 0, 1, 2, 3, 4, or 5, and this is the real class 0, 1, 2, 3, 4, 5. So this one was predicted to belong to class 0 and actually belong to class 0. This was predicted to belong to class 1 and actually belong to class 0, and so on and so forth. So the numbers in the diagonal mean that the predictions were correct, and outside of the diagonal mean that there was some confusion. You can see close to the diagonal that the confusion was between similar classes. This is the best human observer. Okay, and as I was saying, we asked deep learning networks to do the same thing, and we got way better accuracy than human experts had. So for example, the best classification accuracy for humans was 55, the best for deep learning networks in a first stage was 76%. So way better classification for deep learning networks than for humans, with a similar pattern of confusion, with similar classes being confused, but way less. In total, fewer errors. We even use some techniques, data mutation, where we manipulated the training set and we got even better results, almost getting to 80%. We also kept an eye open for practical usability of this software and paid special attention to make the training and testing data as independent as possible by dividing our data collection site in 4 different points to make sure, in 4 different areas to make sure that the data that we use for training and the data that we use for testing was not even close and was as independent as possible. And even in that case, we ended up with percentages way over human accuracy, higher of 76 and lower of 68%. So in a problem that is very difficult for human experts, 55%, these are not regular people. Regular people, the computer vision beginners, some of them got really bad results. The computer vision expert or the forestry expert, best result was 55%. And deep learning systems can help speed up surveys because can process data way faster than human people can, and they can get better accuracy, way better accuracy. Not perfect accuracy, but better accuracy. Expert input is still needed. Someone has to do the initial annotations to train the network. Someone has to go and have a look at the results and say, okay, no, here, this is probably not correct. Okay, some expert needs to check that. And in order to check that, probably going to the field is necessary or is helpful, or being able to look not just at the picture of every bush, but look at the context in which that bush is. This is a little bit of a more time-consuming process. But even taking that into account, having a deep learning system that can get it about 3/4 right can probably help speed up surveys of this type of sites. Okay, so in this case, deep learning has a real practical potential to help forestry researchers obtain better results in their studies.